This is going to be an example of working a design of experiment problem. Assume that you conducted an experiment to determine the effect of gas velocity and fluid viscosity on a dimensional factor K related to the pressure drop across a screen plate used in bubble columns. So let's take a look at what we have. We have two variables. We have velocity and we have viscosity. And we're going to vary them at two different levels, a lower level and a higher level. So what we have then is a two-factor, two-level design. So first of all is the levels, two levels and two factors. So this is a 2 to the 2 design. Normally, a 2 to the 2 without replications would be four runs, but we made 3 reps. So in fact, we actually have 12 data points. So first of all, we're going to start by calculating the contrast for A, B, and AB. Now, you can use the formulas, but what I do is I just use these columns because that's where the formula is in there. So let's take a look at column A. So we've got high, and then I'm going to go over here to the totals column, high and high. So out of those 3 reps, I created a totals column. So those are the 2 totals where A was high, and then these are the totals where A was low. So remember, for a contrast, I'm going to take the highs minus the lows. So I can start off with 55 plus 72.4 minus the lows, 55.8 minus 75.8. And that is equal to negative 4.2. Contrast B. So let's go ahead and follow in with the same thinking. So for the highs and B's, they were these 2 runs. So those are the totals, the high ones. And then the 2 low ones are these. So high minus low, so that's going to be 75.8 plus 72.4 minus the lows, 55.8 minus 55. And that is 37.4. And then we have the interaction. And just in case you missed it in class, remember we were able to design the standard form or generate the standard form, the standard design using Yates. So the interactions come from just multiplying the 2 columns together. So negative, negative, positive, positive, negative, 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 positive, negative, positive, positive, positive. So that's where that comes from. Then we have, to finish, so our AB, so for the AB interaction, these are the high ones, so high, and then the low ones are these 2. So high minus low, so we've got 55.8 plus 72.4 minus, oops, that's a 5, 55 minus 55 minus 75.8, and that is negative 2.6. So those are the contrasts. All right, now let's go ahead and go to calculate the effects. So for the effects, I went ahead and put our formulas in here just to make it easier for us. So you might, have them handy for you when you're going through a design of experiment. So we're going to take the contrast and divide by n, 2 to the k minus 1 for effects. Take the contrast squared divided by n, 2 to the k. So please keep in mind that the numerators are different, and then we square the contrast for the sum of squares. So let's go ahead then for n. This n is, this one right here, is the number of reps that we ran. So n is equal to 3, and then k is equal to the number of factors, so that's 2. So for our contrast, then we have 3, we have 2, and then 2 minus 1. So that's going to be 6. So we'll take the contrast and divide by 6. So for A, it was negative 4.2 divided by 6, and that's equal to negative 0.7. For B, it is 37.4 divided by 6. That gives us an effect of 6.233. And then the AB, our contrast was negative 2.6 divided by 6, and the effect is negative 0.433. Let's give that just a little bit of thought. We said initially when we began talking about design of experiments, what we want to know is the effect of changing a variable from one level to the other. So and we thought, well, let's calculate then that the average at high minus the average at low. Well, that's exactly what this effect is doing for us. And the average, if you think about it, well, why 6? Well, because we had 6 times where A was high, 6 times where A was low. Out of those 12 points, half were at the high level, half were at the low point. So that's where that 6 comes in. Okay, so those are the effects. And then let's go ahead and calculate that. Well, let's go ahead and move down to this. As long as we just calculated the effects, let's fill out this table. So I'm going to go ahead and write in negative 0.7, 6.233, and negative 0.433. So those were the effects. From the effects is where we can calculate the coefficients for our regression equation. And we do that by dividing by 2 for those 3. So negative 0.7 divided by 2 is equal to negative 0.35. 6.233 divided by 2 is equal to 3.117. And then the AB is divided by 2 is equal to negative 0.2167. So then what about our coefficient? Well, the coefficient, that turns out, it's just going to be the grand average. The grand average. But I want to show you something. We can also, if you think about it, the highs and the lows, these are all ones. This is my y-intercept, that this column right here. We think of that as our, well, it is there because that's how we would calculate then the our y-intercept. And you know, if we weren't using software or doing these equations by hand, we can solve these using linear algebra. So we need to have the column in there to actually end up with a y-intercept. So we can take these as plus, 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 since these are all 1. But I want to have the average for the coefficient, so it's just going to be the grand average. So essentially, take this, and this should say grand total. That's not an average, that's the grand total, isn't it? 259. So our coefficient then is going to be 259 divided by 12. So the total 259 divided by 12. And I actually have to look up what that is quickly. Let me calculate that. So 259 divided by 12. So our grand total divided by the number of data points that we have. So 21.58. So our regression equation then is y, and we put the hat on because we're making predictions, 21.58 minus 0.7a. I'm sorry, I pulled out of the wrong column. This is the coefficient column. So 21.58 minus 0.35a plus 3.117b minus 0.2167ab. So that's the coefficient for the interaction term. So let's just put it to use. How do we use that then? So if we were to say, let's set A to low and B to low. So they're both set to their low value. Then what we do is we substitute in a -1 for the low level and a +1 for the high level. So 21.58 minus 0.35 low level plus 3.117 low level minus 0.2167 and lows. Then you just solve for that equation. And when we do that, we get 18.6. So that would be the predicted value if we set the velocity and the viscosity to their low levels. All right, now we need to go back and finish off calculating our sums of squares. So sums of squares, contrast squared divided by n to the k. So n, number of reps is 3, 2, and then we had 2 factors. So, so that's a 2. So n, 2 to the k, where k is the number of factors. So 2, so that works out to be 12. So sum of squares for A, negative 4.2 squared divided by 12. And that's 1.47. 37.4 squared divided by 12, 116,563. Negative 2.6 squared divided by 12, 0.5633. All right, so now we have the values to enter into our analysis of variance. So we're ready to put these into our table. So I'm just going to recopy them here. The sums of squares and 0.5633. All right, so we have one value that we still need to calculate, and that's this total. So the formula for that is it's going to be, let's go back up here, is it's that tedious one where we're going to take and square each of those values, and then from that, we're going to subtract the grand total squared divided by the number of data points, so 12. So sum of squares total is equal to 24.2 squared plus, let me make sure that you can know what I'm writing there, plus 28.9 squared, and then on till we get to the last point in our data set squared. So that's the first part of the equation. From that, then we take off the grand total, so 259, square that, and divide by the total number of data points, 12. So if you work out those numbers, that is actually equal to 5830.92 minus 5590.08, and that works out to be 240.8367. So that's the sum of the squares total. Tedious, but not difficult. So we're going to put that into here. 240.8367. All right, so the only one that remains then is the error. So sum of squares total, so sum of squares error is equal to sum of squares total minus sum of squares A minus sum of squares B minus sum of squares AB. So take the total and then subtract off those three. And what remains then is our sum of squares error. So when we do that, we end up with 122.24 there. All right, so now we have to enter our degrees of freedom. So for A and B, it's this one is A minus 1, B minus 1, where A is the number of levels for factor A, B is the number of levels for factor B. So we ran both of those at 2 levels, so degrees of freedom are 1 for both of those. This one is A minus 1 times B minus 1, so 1 again. And then for the total, it is equal to the number of data points, number of experimental runs that we made, minus 1. So we made 12 runs, so that's 11, which leaves us then for error 8 degrees of freedom. Mean square. So mean square is equal to sum of squares divided by degrees of freedom. So 1.47 divided by 1. 116.563 divided by 1. 116.563. 0.5633 divided by 1. And then the error is 122.24 divided by 8. And that is 15.28. So the only thing that remains then is for us to calculate the F values for our factors and interactions. And so F is equal to mean square of the factor divided by, whoops, that should be an M, mean square error, mean square error. Whoops, mean square error. Let's try another one. Mean square of factor B, mean square error. And then the mean square of the AB interaction, mean square error. So that one is going to go here, this one's going to go here, and this one's going to go here. So this divided by the error, this divided by the error, this divided by the error. Those are our F values. So this one is 0.10, 7.63, and 0.04. All right. Now, these, remember, are position. This is position data. So we have to go to our null hypothesis and recall that for the null, we essentially have 3 of them, one for each, for A, for B, and for C. Essentially says the factor is insignificant, or you can even say the coefficient for A, which would have been, I think that would be B1, is equal to 0. So essentially, the factor is not significant, not important, is not significant, not important, is our null. So B, not important. Lots of ways you can word that, but essentially that's what this is meaning. C is not important, not significant, not important, doesn't influence our Y. The coefficient on the variable is equal to 0. So that's those are our null hypotheses. So now we need to look up our critical F. So just for a change, I chose alpha is equal to 0.01. So we can look up and see what it is when we have a different alpha. So 0.01, and then we have degrees of freedom for the factor, degrees of freedom for the error. So we need F, alpha of 0.01, 1, and 8. So go to the F table. So this is the alpha equals 0.01 table. The numerator degrees of freedom are, the columns, and then the rows correspond to the denominator degrees of freedom. So we had one factor for our one degree of freedom for A, 1 degree of freedom for B, and 1 degree of freedom for AB. So 1, so we're going to be in this column, and then we have, for the degrees of freedom for the error, there were 8. So we want this value right here, 11.259. So our critical value is 11.259, if I remembered that right from switching. Okay, critical value. Now we put our evidence on there. So our evidence for A, we had essentially 0.1. So here's A over there, 0.1, A. AB was even smaller than that. So it's like over here, that's the interaction of basically 0.04. And then for B, it was 7.63. So B is somewhere more around here. B, and its F value was 7.63. So given the null is true, G and T, the evidence is not surprising. Now, you would examine these separately, right? Because sometimes you might have one factor significant and the others not. In this case, none of them are. So G and T, the evidence is not surprising. Do not reject the nulls. And that goes for all three of the nulls. Do not reject the nulls. So what this tells us then is that going back to our scenario, the velocity and the viscosity are not significant influencers of K. Thank you for watching the video. I hope that it helped.